the point P. Point P lead to point Q, and the same point P lead the Q prime. You see? That's why the origin is the point P. You see? Now, x1, x2, attention now, is approximate point belongs to this charge. Now I'm talking about when, attention now, you see, you have a point. You choose, as I said before, around a point, okay, a region over here, okay, just close to this point, this is a mapped point, and then I apply the inverse, okay, then I have a bunch of points here, which this region over here, okay, belongs to the vector, the tangent vector space, as I said. You see? Now, then I'll apply, it's important here, that these points over here, they are approximation of the points on the manifold, as I insist repeating, you see? So, they are not the same, but they are approximation. That's why this range over here is quite close to the Q and Q prime. It's quite close, see? Because I want to set, okay, at the point P, a plane, in this case, this particular case, this is not a plane because it's M2, but a tangent is called tangent vector space, see, as I said before. So this figure here fits on the tangent vector space, okay, as I said. So all the points here are approximated points from the manifold. So I repeat here, see, x1, x2 here, approximate point belongs to the chart U. y1, y2, approximate points belong to the chart V. Chart U and V belong to the same tangent vector space, see, the same. The chart U and V provide representation of the same tangent space, TPM, of the point P, at the point P. Attention now, if I choose another point for the manifold, all these calculations, they will be different, because I said points in the manifold are a labeled point. See, you cannot sum, you cannot take the dot product, nothing. Okay, that's why I will be based on the tangent vector. See, the tangent vector can do anything I want because it's Cartesian coordinates. You see, but it's a very close region around a point P. See, if I have another point in a manifold, there will be a different, okay, tangent vector space. All points have its own tangent vector space. We call a bundle. Okay, a bundle is a set of all the tangent vector space. Now, then I repeat, the chart UV provides representation of the same tangent space, vector space TPM, of the point P on the manifold, in this case M2. Now, since both charts describe the same local neighborhood of P, attention now, the same local, they define different coordinate bases for the same, attention now, the same space TP M2. The transformation between this coordinate, okay, coordinate system, is given by the transition function I call f sub I. F sub I takes a point here, approximated point, okay, and transform on the same point using the base y upper I, 1, 2, 3, or in this case 1 and 2. Now, GI is just the inverse mapping, okay? They transform points, approximated points in the manifold to the y coordinates. See, that's the inverse, GI. So this ensures that in this case, the both coordinate system are valid description of the same underlying tangent vector. I repeat both. I repeat here. No problem. This ensures that both coordinate systems are valid. In this case, okay, description of the same underlying, okay, that's the same underlying tangent vector space. I think that's clear. So, if you have a computer program, see, you can choose points close to Q and Q prime, you see, and then construct the chart green U and the blue chart V, okay? So you work on that. Attention now, this chart here, both the charts are quite close to the point P. Okay, that's important. Just to fit the tangent, the tangent vector space. You see, because you substitute. You see, you have a tangent, you have a surface, you have a tangent. You see, so you have to choose points close to the point P to approximate. You see this example, you see, clarify more what you have been done. Okay?